what is this limited by? What is the what stops you from getting even larger numbers?
Dirt.
Hmm?
Dirt.
Yeah, basically, so charge scattering, charge impurity. So you have some dirt even in the suspended device and even in this device. So what they do is something different. Imagine you now apply, you put next to your device, like literally a nanometer away, you put another flake of graphite. Okay? Basically, if now you have a piece of charge impurity here, there will be a mirror image of it below. And the effect on the electrons will almost cancel out, unless they are about 1 nanometer away from this charge impurity. So if you have a screening layer, very, very, very close proximity to your graphene device, you can actually make the mean free path ridiculously long. Okay, so this is a mean free path of hundreds of microns. There's a question mark here because, of course, you cannot measure it. Like making a device like this is extremely hard. Okay, but you can measure, or at least estimate the mobility and find it to be on the order of 10 million. Okay, and this is already comparable to what you get with gallium arsenide, the best gallium arsenide samples. So this was 30 million for gallium arsenide. This is more or less on the same level. And again, hundreds of microns of propagation. This is a very, very rough approximation because this one you can measure. Okay, you can measure mobility. There's nothing, at least the way I define mobility, when I'm talking about like whole mobility, but you cannot measure the mean free path very easily. Okay, is all of this clear? Raise your hand if you're following. It's clear. Okay, good. Let me confuse you now. So it actually, yeah. So the mean free path is limited by basically device size. Okay, but let me actually now go ahead and confuse you, because this is a lot more complicated. Okay, because there's a few other definitions you want to measure. So first of all, we have the mobility, which is we talked about now at length. We have the residual charges. So this n star, which is the minimum level of charge disorder that we have. And then we have the mean free path, which is or equivalently the transport length, okay, which is the mean free path between scattering events, or at least that's what I told you, but that's actually very incorrect, okay? What the mean free path in 2D materials is defined a bit differently, okay? It's not exact because mean free path between collisions is kind of ill-defined, okay? And it's not what we actually care about. The mean free path, as indicated by the name L transport, what I showed you in all these tables, okay, is the mean free path between collisions which impact transport. Okay, so for example, imagine I have two electrons colliding in a way which doesn't impact transport, okay, because their momentum is conserved. Okay, so the total amount, the charge that moves around my system is conserved. This will not change the mean free path. However, so what I'm measuring when I'm talking about mean free path for transport is actually it's a mean free path between specific types of scattering, specifically large angle elastic scattering, such as from charge impurities or edges. Okay, so if I'm going through a charge impurity and I'm scattering back, then I'm giving that impurity some momentum. Exactly. If I have a low angle scattering, okay, that probably is unimportant. And low angle scatterings are much more frequent than usually in some regimes are much more frequent than large angle scatterings. Okay, it depends on the case and whatever, but low angle scattering, not important. It has an impact on the quantum wave function, but it's not important. Whereas large angle scattering from charge impurities or edges, okay, that will mix the momentum. So I can lose momentum to when I scatter from the edge. So for when I'm measuring the mean free path, when I'm measuring mobility or like
What is so special about edges? Why is this?
no, anything that can scatter momentum. I'm just saying in a real sample, okay, the edge is like an area where you're breaking the translation symmetry, obviously. So momentum at the edge is ill-defined, and you can scatter, you can hit here with one momentum and come back with a different angle, or if the edge is not perfectly straight, you can come here and come at a weird angle going out. So you can lose momentum to the edge. Likewise, when you scatter basically over any potential, okay, what you're really doing is you're scattering from, you're giving momentum to the lattice, but it's kind of a very tiny amount of momentum and the lattice doesn't care. But this is not momentum conserving. So,
what's the difference between L phi and LQ?
Give me a second.
Okay.
I'm not there yet. I said I'm trying to confuse you. So it's not that easy. So the other quantity I have is then the phase coherence length, which is basically the mean free path between inelastic scattering, like electron-electron scattering, and electron-photon scattering, and basically that's it. But I put ETC in case I forgot something. So what does this mean? Imagine I have like your Dirac cone, and so it's like this. I'm sorry, I don't have anywhere to draw. Oh wait, maybe I can. Okay. You have your Dirac cone. You have an electron, okay, and it scatters from another electron. They can change their energy. Okay, the total energy and total momentum is conserved, but they can change their energy and momentum. So this is an inelastic scattering, and that basically can mix up the phase. Okay, so if you're thinking about like if the first mean free path, okay, and you have like some charge disorder here in the middle, okay, so there's like a blob of dirt, okay, your electron is kind of coming here and then it's scattering at some angle. Maybe it's a large angle, maybe it's a medium large angle, okay, but it's scattering. This is a coherent process. If there is nothing, the phase of the electron, okay, coming in and going out is well defined. It could be complicated. Maybe the electron comes here with like a plane wave, it's well collimated, and it comes out looking like garbage, okay? It's looking very complicated. But if you do this experiment 1,000 times, it will come out with exactly the same garbage-like pattern every time, okay? So this is coherent. There is nothing time-dependent about it. There is no ambiguity in the phase. Whereas if you do this experiment and you're scattering from something like another electron or a phonon, okay, even if the total momentum is actually conserved, okay, electron-phonon, like it could be like electron-electron scattering is conserving the total momentum, but the phase is scrambled. So because you're mixing the phase of the two electrons, and then you can end up, if you do this experiment 1,000 times, you will get 1,000 different results. Okay, so these are two completely different things that we're both thinking of them when we're talking about the mean free path. Intuitively, when we're talking about the mean free path for real, what we're thinking about is the Dingle time. Okay, so this is just a scattering length between anything. Okay. The only problem is that the Dingle time, okay, named after Dingle apparently, is something that's kind of, we'll get to it later, okay, but it's something you encounter in Shubnikov-DeHaas oscillations. It's not something you usually measure for your sample. And it's also not necessarily important, because if I'm doing electron optics experiments, I have a waveguide, for example, trying to draw somebody's attention. So if I have a waveguide, then I don't care if there's, I don't necessarily care as much if there is some elastic scattering from charge disorder in the device. I care that if there's some contamination. What I really care about is something that destroys my phase. makes it the process the transport incoherent. So this part, okay, is less relevant than the phase coherence length. On the other hand, if I want to make a really good transistor and make billions working in the industry, well, maybe I don't know about the billions part, but anyway, then I care only about the mean free path. And if I'm doing magnetic transport experiments, that's the only case where I care about the total scattering length, which is what we usually think about. So this is, just because this is a fairly complicated or let's say nuanced discussion that's very easy to miss, I just wanted to go into this in a bit more detail, so you have this glossary now. And there is one more thing which is worth mentioning here. There is also the thermal averaging length, okay, which is basically the kind of the length scale associated with the energy scale associated with the temperature, which in our case the temperature is most of the time is going to be near zero, so this is infinity. Okay, but like you can ask yourself how important this is, and sometimes it is important, just not at low temperatures. Okay, questions so far? Should I confuse you further, or are you okay? Okay, let's just to go into this a bit. Okay, so basically just repeating what I said, the mean free path is controlling the resistance, is controlling the quantities I measure in transport directly, and but it can give you very complicated phase fronts. Okay, if you have a lot of scatterers inside, but not dephasing. Okay, whereas this L phi, the phase coherence length, controls interference phenomenon, and we'll hopefully mention how to measure this in future classes. Now, typically, okay, like historically, you could always say that L phi is almost always larger than L transport, which is always larger than LQ, which is just scattering from anything. So of course, this is larger than this. But today it's no longer so clear. So you can also run into situations where the phase coherence length and transport length are comparable, or even, it's not so obvious which one is larger. Okay, so that's. But just to make sure that when you're saying mean free path, or you're thinking about mean free path, you know what to look for, what to think about, because and you'll be surprised how many papers there are that are confusing all these concepts and making a mishmash, which is not always justified, because again, you can have phase coherent transport, which is definitely larger than your device length, okay? Whereas, and you can have, whereas the MFP, so I just want to emphasize this. When people say MFP, almost always they mean this guy, transport length. Okay? So you can have a device that has a limited mean free path, okay, if only because the device is small and you cannot determine if it's larger than the size of the device, but the phase coherence length can be much larger than the device itself. Okay, so it's just be careful what you're referring to. Now, we can go back to the table again and now fill it in with the sizes. And as you can see, the phase coherence length, this is a very, very rough estimate. It's also not really available for all of these quantities, so I'm just throwing numbers. Like not all of these, but like I don't know if there's actually measurements for phase coherence length for CVD low quality devices. I don't know why that would be interesting, but maybe. But you know, it should be on the order of half a micron. Higher quality devices give you, give you longer mean free paths, and they're generally quite large. Okay, but and definitely larger than your device a lot of the time. And all this is really to justify discussing electron optics, okay, which is in the future. And now we're off to a different topic, slightly different topic, which is magnetotransport. And first question is, what are we seeing here? What are the bees doing?
The bees are in the
Simple,
bulbs,
yeah.
rotating, and
Yes.
along the edge,
Lambda
there's
levels.
the edge states. So
Yes, very good. So we have edge states and lambda level bees. And there's a magnetic field. Sorry if it's hidden by the table. I definitely had...
you can see on the TV screen.
yeah, exactly. You can see on the TV screen. So I had a lot of fun making this slide, and that's the important part. But except for me having fun, what is the motivation to learn about about magnetic transport in this context? So one reason is this dingle time I keep mentioning, just because it's fun to say dingle. Magnetic transport basically is dominated by Shubnikov-de-Haas oscillations, and that basically tells you that there is when, and only when, so there is something called Shubnikov-de-Haas oscillations, and I'm about to tell you later in this class what these Shubnikov-de-Haas oscillations are, okay? But we want to know what they are because if you see these Shubnikov-de-Haas oscillations, it means that the magnetic length is smaller than the mean-free path, and the other way around. So, for example, okay, if I have a device taken from a real paper, and even a high impact journal paper, no, it's actually a really nice work that has nothing to do with the topic, but I'm just advertising it here because they have a really nice plot where they show the same device at 10 Kelvin, 50 Kelvin, 100 Kelvin, 200, and so forth. So what you can see here is for 10 Kelvin, you see these oscillations. You don't know what they are, but these are Shubnikov-de-Haas oscillations. Okay, trust me on this one. And on 50 Kelvin, they start, let's say, here you can kind of see them going down to around 1 Tesla-ish. Okay, here you can start seeing them maybe 2.5. You go up in temperature, and actually they kind of start at 100 Kelvin. They'll start somewhere here. Okay, and if you want to see them at 300 Kelvin, the same oscillations, they will only appear for really high magnetic fields. Okay, so I can also define mu mobility for dingle or Shubnikov-de-Haas. Okay. There is only one problem with this. Can anyone guess what is the issue with measuring mu dingle? So where are these oscillations starting?
Around 1.2 Tesla.
Yes, that's a very good answer, except it's around. What do you mean around? What's your precision? So this is a kind of a qualitative way of defining things, okay? Like I can tell you, yeah, it's kind of starting around 1, okay? But maybe it's actually around 0.9, 0.8. There's a lot of error here, okay? It's not you can, and like in a clean sample like this, okay, you can say, oh, okay, I'll just look at when this thing becomes below a certain, the height of the oscillations. It's like I can trace where it goes. I can do, yeah. For a very clean sample, this is well defined, okay? But this is kind of, I took this example because it's a very nice plot, okay? In a real sample where there's a lot of stuff going on, okay? It's not so easy determining where exactly this starts, and you really have a problem that it could be 1.5 Tesla, 2 Tesla, 0.5. Also so this is not a real good way to measure, okay, exact quantities, but on the other hand, it does give you something which is related, okay, to the mean free path. Not to the mean free path in the, let's say, intuitive sense of time between or length between scattering events of any sort, not just elastic, inelastic, just any type of scattering event. So yeah. So this is really not a good way to measure mobility. Okay, but it is a good way of giving you motivation, I hope, as to why you want to know what Chudnikov-Das oscillations are and what to do with magnitude transport, and more generally, we want to look at all of the cool physics, such as zero-order Landau levels, which hopefully we'll get to today. Maybe there'll be some leftover. That's it. Or at least start. Okay, so recap, magnitude transport. We already saw this today. Okay, it was the same drawing. And we all love Hall effect, right? Who here loves Hall effect? Who doesn't love Hall effect? You don't love it? Okay. It's a good thing you're not taking the class officially, because otherwise you would flunk right now.
He's your student, and just remind me. He's your student.
Yeah, we'll see about that. Anyway, so we all know and love the Hall effect. It's worth mentioning that the Hall effect, okay, is actually one of the features of it, okay, which was kind of known where people were actually doing experiments in this type of physics, and now we all forgot about it, is that it's very independent, okay, of the exact geometry of the sample. If you punch holes into your sample, it'll still show you the same hole conductivity. Okay? Like you can show it, it's basically like if you punch holes, then basically as long as like the sample is not completely disconnected, the current kind of goes around these things and it accelerates and deaccelerates, and the overall tendency to go from here to here is the same. Now, when you're taking your field and increasing it further, okay, you should reach into the situation. This is basically like the cyclotron radius, okay, cyclotron motion. So electrons are coming from here and then they're incident on this electrode. Fine. If you're now increasing the field further, at some point the radius becomes smaller than the sample. Okay, so you start doing like circles inside, so cyclotron orbits. I think you've heard about this, and which leads us to the quantum Hall effect. And again, you were supposed to see this with Jonathan. Raise your hand if you feel comfortable with quantum Hall effect. Okay, so I'll go through it quickly, okay, just in case, but feel free to expedite me if it's, or tell me to slow down. It's completely fine. You can always blame Jonathan. That's what I do. So when you have cleaner samples, lower temperatures, and higher fields, you'll start seeing Landau levels form, as shown in this caricature. Okay, and these Landau levels basically give you these oscillations in the resistivity or conductivity. This is the resistivity. These oscillations, step-like oscillations in the whole resistivity. So you're reaching these plateaus. Okay, and let me run this further one more time. Sorry. Okay.
It's whenever one of the bands crosses the Fermi energy.
Yeah. So this is a really nice video, really nice plot that most people do not understand. Maybe today, at the end of this class, you will understand it. Some of you will understand it a bit better. Some of you are maybe experts on the topic and can teach instead of me, but maybe, I don't know. But there's a few questions you want to ask and keep in mind, okay? Which is, for example, what is the width? So, like, sorry, too many screens. So what is this width? So you just said yourself, whenever you're going through a Landau level, okay, you reach a plateau. Could be. Any more guesses?
Disorder. Disorder.
Mm-hmm.
What's the above?
No, so thermal fluctuations are not relevant.
Okay.
There is no thermal There's no temperature in this plot. This is like a...
It says cryogenic temperatures.
Yeah, exactly. The temperature is effectively 0. So, and it's really related to disorder. We'll go back to it in a bit. Likewise, what determines the size of these plateaus? So why do we have, like, it's this much and then there's a sharp drop? Like, what is the angle of this drop? What is the length of this plateau? Okay, what's going on? So just a few questions to keep in mind. This is again related to disorder. We'll come back to this. And also, what happens to a holy sample? Not like holy like the Pope or rabbi, whatever you prefer, Qadi, I don't know. So holy like it has holes in it, okay, like the ones I showed you a bit earlier. What happens in that sort of a sample? Okay, so to figure it out, let's derive this. Okay, it won't take long, I hope. And we'll start with regular 2D electron gas before switching to graphene, which is different. Okay, and then you can appreciate the differences. So minimal coupling, everybody remembers we talked about this. Okay, so I'm just putting in, instead of having the momentum, I'm putting the momentum. This square should be on the outside. P minus EA squared. Now I'm going to work in the Landau gauge because that's convenient for Landau levels gauge. And the Landau gauge just means that my vector potential is 0 in the x component, x times b0 in the y component. Quick exercise, take the curl of this. Okay, great. You've all convinced yourself, I hope, that the curl of 0 is like this, is like 0 in y and derivative of x b0 in x, so you have b0 field. So this makes sense. Great. Now I'm plugging this in. What do I get? I have basically the x component of the momentum squared over 2m plus this term, which is the only place which is different. Okay? And I can identify like that this is basically looking like, so if you were just to see this, what would you think? I have something which is proportional to momentum and something in x and something which is proportional to x squared up to some shift, py. Do you see this? So I can actually do this formal exercise. I'll call this px squared over 2m. This is my momentum term in x. And then some coefficient goes out and I have x squared shift, or the x term squared, shifted by something which is proportional to ky. So for every ky, basically, because this Hamiltonian, it will commute with py. Okay? It will not commute with px, but it will commute with py. So I can separate like this kind of degree of freedom outside. It's symmetric in y, and therefore I have something which I can call all of this thing, call it by some, this is my shift, and this is x. Great. Oh, and I can already take this opportunity to identify this e squared b0 squared 2m to be related to something called the magnetic length. Okay, so magnetic length is just h bar over e b0. If you're really bored, you can check the units and see it's really length. It is, I think.
Should be an I somewhere.
Sorry?
Is there an I here?
I don't think so. Like it's length, so it has to be real.
Yeah.
You mean here?
Yeah,
Or,
exactly.
Would be near the QY.
Next to the H bar, there's the 9, right?
No, because you did a
This is
square
squares.
and it's a derivative of an e time.
Squared, yeah.
You're right, but it's a derivative of exponent to iky, so the two i's are just gonna be negative.
this is why you have yes.
K just defines the center point, right?
Yeah. So this is the center point of what is this? P squared plus x squared.
Harmonic oscillator.
Thank you. Ding 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 or dingle dingle dingle. You get 3 points. Not to the grade, just to your self-esteem. You identified an harmonic oscillator. This is exactly what we have. We call xk the shift lb squared times ky. Okay, and then all I have here is an harmonic oscillator around this point. Okay, around this xk, x of k. Clear? So, and if it's an harmonic oscillator, then hopefully I know how to solve it, and I get basically these type. Okay, and then you can see I have solutions to an harmonic oscillator. Okay, so yeah, quantum harmonic oscillator, obviously, but still, it's a fairly simple problem. For different ky's, I'll have different shifts, but other than that, it's basically a simple harmonic oscillator. And what's not mentioned here is what this length is. Okay, so this is a universal quantity, so it's actually worthwhile remembering. It doesn't matter if it's graphene or silicon nitride or, well, silicon nitride is an isolator, but free electrons, silicon, anything, metal, whatever, magnetic length is always this quantity, 26 nanometers over square root of b in units of Tesla. So if you have 4 Tesla, the magnetic length will be 13. And so forth, okay? So it's just useful to remember. Now, what do you get? Okay, so now you have basically for different locations, okay, in the sample, I can have different lambda levels. Again, this is a solution in x, so this is the x-axis, and this shift is also in x. So I will have like a set of different harmonic oscillator functions at every location inside of the sample, shifted by ky. If my sample is finite, then the units, then ky is basically multiples of 2 pi over L. Okay, so I'm basically shifting in my side of my sample by jumps of 2 pi over L. How many of these guys fit inside of the sample then? How many levels will I actually have? Okay, then obviously, I mean, I can have, I know how many shifts I can have. Okay, it's just that's determined by the length, but that's but the question is what mode will I occupy? If I now start applying field and I change the carrier density, am I going to have one mode with all of the electrons, or how are they going to be distributed? How are they populated? So to know that, I'm reminding you, or you can actually see it quite clearly, I hope, that the area of each wave function is going to be L, the width of the whole bar, okay, times 2 pi over L, okay, which is the times LB squared. This is the thickness of the Landau level strip. Okay, remember, your shift, okay, is LB squared times KY.
So there's something wrong in the next slide.
Mm-hmm.
It should be 2 pi over L times LB squared or something?
No, K
2 pi over L is 1 over
is KY, so the location
but
of...
it's x naught plus something that is...
So X is okay, forget about the slide for a second. X is shifting by LB squared times KY. So LB squared times 2 pi over L.
So this is what I'm saying. So
So we agree.
Okay.
So I'm saying this is the thickness, sort of, okay? Order of magnitude is like this, and the width is L. Hand waving approximation, I have an area of L times 2 pi over L times LB squared, so 2 pi over LB squared per level. Now, I want to know how much flux do I have going through the sample, okay? And I want to basically ask how many levels do I have to occupy for this to happen. And what I'll get is basically the entire flux is 0. So I end up with the per one of these levels. I have so 2 pi LB squared. I'm plugging in the expression for LB squared I had before, which was H bar over EB0. That's LB squared already. Okay, so H EB0, B0 and B0 cancel, and I end up with just H bar. Sorry, and 2 pi H bar becomes just a Planck constant, not H without the bar. So H over E, that's something defined as the quantum flux. Okay, so you can do this in a more regular way. Probably, I'm hoping Yonatan did it in a slightly slower and more detailed fashion. But you get that in every strip, okay, every slice of your sample, you have an H over E flux going. This is the quantum flux for, I think, obvious reasons. Now, I can therefore, if you tell me I have the total flux going through the sample is some B0 times the entire area, then I can tell you how many electrons are going to be filled, or what's going to be electron filling density, okay, which is also called the filling factor. And now I can tell you if I start filling up the sample. So in the beginning, I'll have some of these levels filled, okay, and then at some point, I'll have enough flux to fill. As I increase the field, I'll have enough flux for 1 per Landau level, 1 per slice, okay, and then I'll start filling the second level. Okay, if I keep it in terms of the flux, at least. Now what do I have here? So now I want to look at conduction. What do? I apply voltage here. What's going to happen? If I didn't have any lambda levels, I have no, if I didn't have any B field, I would just have current going through. Great. Now, the bulk modes are localized, but hey, I showed you the plot before, you had finite resistance. It wasn't going to infinity. So, again, these are harmonic oscillators. If you remember what the wave function looks like, it's localized around this part. And then there's another jump and another localized wave function. So this should be extremely resistive. And moreover, this is just the cross-section in X. Why is there resistance in Y? So what is rho xy? It means I'm applying voltage in X, or applying a field in X. Now I have currents going up. So I have here kind of a weirder observation that basically, you have electrons. The resistance in the quantum Hall experiment is actually, let's go back for a second. Like, this explanation makes perfect sense, except it's not making any sense. Because if you look at it, this is rho xx. It's going to 0 between the levels. And then it has finite peaks. If I have localized modes, I should have infinite resistance and no conduction. It definitely shouldn't go to 0, which, if you have resistance going to 0, it means it's a really good conductor. What's going on? So again, my purpose in this class, I hope it's clear by now, is to confuse you further about things you thought you knew. Okay? How am I doing so far? Raise your hand if you're confused. Okay. So, quantum Hall effect, it sounds like we all have this kind of this intuitive picture, okay, where electrons are going around in cyclotron orbits, so they cannot go from here to here except through these skipping orbits, okay, whatever they are, okay, but we'll get to it in a second. But like, if electrons are in the bulk of the samples are going around in circles, there's two questions you can ask yourself. Why is there any like zero resistance in X, let alone or finite or even really small resistance in X? And even stranger than this, if the electrons are all doing like this, which I didn't show you. I mean, if you go back to the expression, like I want to clarify that I'm okay. I showed you the solutions are basically, what do they look like? They're going to look like harmonic oscillators in X, and in Y it's a plane wave. So I didn't show you any cyclotron orbits. If you want to, these will behave as cyclotron orbits. Okay, you can show this. You'll have to this is kind of a static picture where you have a spread out wave function. You can show that this leads to motion of electrons that looks like a cyclotron orbit, but it's clearly not this exact motion. Okay, because if the electrons are just going around, just think about it. Like, this is also, forget about quantum Hall. This you do not even understand, or this is confused. This is not even the right picture for classical Hall effect. If the electrons are keep going around in circles, they never reach this edge.
Well, we created it translationally symmetric.
Sure.
That very much affects the fact that they.
Sure, I'm just saying the intuitive picture you have of electrons going around in circles is not true even in the classical limit.
Yeah.
But you have electrons at the edge, and they can also move under some electric field and magnetic field.
It's okay.
No.
Most it's like the type of thing that's very easy to miss about how classical Hall effect is working. Let's go back to it for a second. Okay, so what is the classical explanation? And the
Lorentz
classical
force.
explanation has nothing to do with electrons at the edges.
Lorentz force.
Okay, let's rederive this. Okay, we'll take a second. And the problem is, okay, the reason we don't actually see, like, the reason I told you that you want to see cyclotron orbits, you will not see them in the static sample, is because you didn't apply a field. Where are the electrons going to go? Are they going to go like this or like that? So to see cyclotron motion, you have to accelerate the electrons in a certain direction. They have to go in one direction. So you have to include non-trivial E. Okay, and this is true also for the classical case. Let's do it in a second, but I just mentioned that you can do this also for the quantum case. You'll get exactly this. It's a bit more complicated, than you have to follow like the center of mass of a wave packet that's accelerated under a field, and you will get this cyclotron orbit. Okay, so this is the classical explanation for for Hall effect is actually really useful. Okay, it'll work pretty similarly also for the quantum limit. But what is the classical limit? So the point is, electrons don't actually move in circles. It's a myth. Okay, what they actually do is like a screw-like motion. Okay, as we're all about to see together, where they do kind of circles, but also drift towards the top at a fixed speed. Why is that? So if you have electrons and there's non-trivial electric and magnetic field, we are governed by these equations. In X, we have m, the mass, times Vx dot. That's the force, Lorentz force, really working on you. sorry, you have a combination of the Lorentz force, which is coming from the B field, and the acceleration from electric field. Now in Vy, you have mvy. This is the force in y. It's just Lorentz contribution. Okay, so these are your two terms. And now I hope you can all open some sort of a notebook and solve this.
And are we solving it for the free or for Druden model?
Sorry?
For free or Druden model?
Free? No. No.
No, not
Free.
free.
Suppose equations.
Trivial. Yes.
No.
Yeah. Notebooks?
Yeah, notebooks here.
You too?
Yeah, I have solved it.
Hmm?
I solved it. I was so
Write it on a piece of paper. I don't trust you. You don't have to, but everyone else does. Grab a piece of paper from someone. Here's a pen. Raise your hand if you're done. Okay. We have a few more minutes, so let me just. I'll just do this really quickly, so you realize how, like, it looks like a trivial expression you've all solved. Maybe it did happen in some exercise, but it's actually really easy to show the drift motion. I'll just plug in this thing into that thing. Okay, yeah. I'll plug one into the other, and basically I'll end up with Vx double dot. Sorry. So I'm plugging in. I'll take the derivative in time of this one. Sorry, I'll take the derivative.
Wait, will you take derivative?
Derivative in time of this one. Okay. Then I have mvx double dot. Okay. Equals mvy dot b, and this term drops because it's not time dependent. So then I can plug in vy dot and get this equation. Okay? And this again is harmonic oscillator, classical one this time. Very easy to get. Great. Now I plug this into the first back into the first. Now I look at the first equation back. What do I have here? I just told you Vx is an harmonic oscillator, so it's time dependent. Okay? Left side is time dependent. Okay? If I'm looking at the time averaged quantity, this is 0. So this is an oscillatory term. And then, so the obvious thing to say is that Vy is also oscillatory. Okay? It has an oscillatory component plus a time independent term. So a drift velocity. So I plug in Vy equals V oscillatory, which cancels out with this term, and then plus a time, just a drift velocity, which is just giving me Vy equals E over B. Yes? No? Okay, so again, I take the time derivative of this, plug in this expression, I end up with something which is an harmonic oscillator. Therefore, I know that Vx is purely time periodic, whereas Vy is a mix of a time periodic component and something else. So the time periodic component, like I can take out if I'm looking just because this thing is time independent. So if I want to see the time independent contribution, I'm just looking at the time. The DC contribution of this is 0. DC contribution of this is some V drift, and I just get this. Okay, great. That was easy. So what we just saw was basically electrons are really doing this kind of spiraling up, screw-like motion. Okay, and this is why they are reaching. This is why you have Rx1. You're applying a field in this direction, but all of the electrons are going up. So they are localized in X, but they are going up. And this is actually exactly, okay, again, I'm not showing you this, but this is exactly the idea behind the quantum Hall effect as well. The electrons are really doing a motion like this and slowly drifting up. Okay, that part of the Hall effect is not quantum, or the quantum Hall effect is like very classical, okay? And what you get is basically that every electron like this has an h bar over E flux associated with it. So the total number of electrons in the sample is B, the total field I have, times E over VH. Okay, that's the flux per, like, E over EA. So B over the quantum flux is B E over H. Okay, and Ni is just the number of electrons in every lambda level. Okay, so This is just my carrier density, and therefore I find that the total current I have up is E times N, and I just found, okay, times Vy, which is the drift velocity, which was E over B. I just found it also, or B over E, or something like that. What was it? B over E, right? Yeah, E over B, like I said. So it was, so the E from, so when BE over VH, the B cancels out with the E over B. I am left with E over ni H E, okay? Or in other words, quantized conductance. My conductance is ni, the filling time factor, times E square over H. E square over H, we already mentioned, is the quantum of conductance. Very important number to know. And basically, so my conductance is taking these steps. It can only take discrete values. What about rho xx? Okay, what's going on there? So you cannot actually understand rho xx in a very easy way. Okay, and why is that? So we kind of like, if this is my is it okay if I steal 5 more minutes, or anyone has to run? Okay, so I'll just try to finish this this part, because so what's going about? Why do I have this strange behavior in the conductance? So first of all, now I have to realize that I do have these edge channels. Okay, I can no longer neglect them. Why do I have these edge channels? You can draw the location of the lambda level inside the sample, and hand-waving version is that it should look like this. So it's flat inside the sample where it's uniform, but on the edges, it's going up. Okay, why is it going up? Because inside the sample, I have a lower chemical potential than the outside. The chemical potential is just basically how much energy I'm gaining when I'm bringing electrons from the vacuum into the sample. Okay, so always on the outside I have less, and like around here it bends, it doesn't just jumps. Okay, so I have this lambda 11, it starts bending around here. So most of the sample, the lambda level is very flat. Okay, but if I start raising my Fermi energy, there is now a cross section at 2 places, this edge and this edge of the sample. So at those edges, I do have modes. Okay, and if I increase the E Fermi further, then I'm going to go through another edge. So now I have 2 modes. Okay, before I had 1, now I have 2 here and 2 on the other side. And these modes can carry momentum, and moreover, they are topologically protected. So, like this is connecting to Jordan's class. They are these are protected edge states which cannot backscatter. So both of these modes are going, let's say, depending on the direction of the field, they will go, let's say, in this direction. Both of these modes are carrying electrons that are going in this direction. And if an electron is here and it's going towards you, it has no way to scatter. There's nothing it can scatter into. So these electrons are topologically protected and cannot backscatter. They cannot hit anything and scatter back because there's no channel for them to scatter into. And therefore, you should have rho xx equal to 0. Okay? Because it's all of the conduction is going through these lambda levels with nothing in them. So,
but it's 0 if you are inside. It's like
0 when you're here.
when you are here. But if you just exactly fill inside some mode, so you are not 0.
Yes. But we haven't finished. Don't worry. Okay. So what do we have? If we're on the lambda level, okay, we have peaks in the rho xx. Okay, because they can have some conduction through the bulk as well. Okay, and things are going in the bulk. So this is the resistivity of the bulk, which it's giving me these peaks. But outside, I only have resistance to something which cannot backscatter. So it's 0. Okay, so And I also have jumps in rho xy because of this drift velocity. Off the Landau level, there is no resistance, okay? None whatsoever, nothing can backscatter. If you have an infinitely long channel, you'll propagate it for an infinite amount of time without backscattering. Maybe something else bad can happen. You can lose the electron, some charge trapping, whatever, but no, it cannot backscatter. But you have plateaus in rho xy because now you have this quantized sigma xy. And this is again not superconductivity, okay? So it's very easy to get excited and think that, oh, we have rho xy or rho xx going to 0. The sample has no resistance. Life is great. And it is great, but it's not a superconductor, okay? It just means there's nothing to scatter to. Now, what about sigma? So we have rho xx, okay? And rho xy, okay? And now what we basically, intuitively, what we found was basically that rho xx equals to 0. So what is the conductivity? If rho xx is 0, what is the conductivity?
It's supposed to be infinity.
It's infinity, right?
Yeah.
Yeah, but is it? Okay, and here's the strange part.
No, but it's a matrix. So.
Exactly. So it's a bit more complicated than that. It's very counterintuitive. But what we'll see together next class is actually rho xx is 0 and sigma xx is also 0. Which is like in a superconductor it goes to infinity, now it's going to 0. Simultaneously with rho xx. Okay, and with that we'll stop for today and continue sometime later.
Tomorrow.
No, because tomorrow we will have a guest lecture.
Ah.
Oh,